Welcome back, Matadors. We're moving on into what is light. Have you ever wondered what light is? Is it matter? Is it energy? Think about what makes up light. Record your notes in what you think light is in this column right here. Now it says with a pair, discuss what you think somebody else thinks that light is. Now, I know we're not in class right now, but maybe ask someone in your house. Could be older brother, or younger sibling, parent, grandparent, and go ahead and write what they think light is. What is light? And then in the third column, something that you would want to share with the class if you could, what you think light is and what you would share about what you thought light was. Light is neither matter nor energy. Light is actually a type of wave, which is perfect because we're in the unit called waves. Light is electromagnetic radiation that you can see, and that is the definition that is written right on your booklet. Light is electromagnetic radiation that you can see, and I have little eyeballs there. So if you go into the slideshow that I also attached to Monday's assignment list, you can see that I've also, if you want to print that out, you can print it, or you can use it to make your own flaps and write those down. But there's the definition of light. Electromagnetic radiation is a type of wave created by vibrating particles. These waves radiate or spread out electric and magnetic fields in all directions from a source. You might recall that waves carry energy. The energy carried by an electromagnetic wave is called radiant energy. And as we go back to our booklet here, our second flap down says radiant energy, and it has the definition there. And I'm going to write electromagnetic waves, and we're about to draw a picture of an electromagnetic wave spectrum. There are many different types of electromagnetic waves. These waves are classified by their wavelengths and frequencies in the electromagnetic spectrum as shown below. The groups include, here we have radio waves, microwaves, infrared waves. Also we have ultraviolet waves, X-rays, gamma rays, and of course light, which is the visible light right there in the middle. Out of the entire electromagnetic spectrum, light is the only waves that humans, like you or me, can see with our own eyes. We can't see any of these other waves. Okay, so in your handout, we want to add to our notes. You can print out the picture that I put in the slideshow, or you can draw your own. And I have the long wavelengths over here, and we see they get closer and closer and closer together. The frequency gets higher and the wavelengths get closer together. And I have written down what they're maybe used for. I just basically copied this picture right here into my notes. The other thing you do want to add is about the energy, that it starts off at low energy all the way to have very high energy. Okay, so those gamma rays are going to be very high energy, whereas radio waves are very low energy. Okay, moving on to page 71 in investigation. What's the use? If light is the only type of electromagnetic wave that you can see, are the rest of the waves in the electromagnetic spectrum even useful? So you're going to need to go on to McGraw Hill and watch the animation about electromagnetic spectrum in order to complete this chart. Okay, you do need to complete this graphic organizer for all the 7 different types of electromagnetic waves. You do need to describe the waves, each of the waves' wavelength. Is it a short wavelength? Is it long? Sometimes they might give you a specific unit of measurement. It might be in centimeters or other unit of length. So you want to write that down. You want to tell me its frequency. Is it a high frequency? Is it low frequency? And tell me about the energy as well. Is it high energy, low energy? And then over here, you want to give me an example of how it's used. How would you use that kind of wave? How do we use it? Okay, so here's radio waves. Tell me what the frequency is. It high, low? Energy, high, low? And tell me how long are the wavelengths? Same with microwaves. High, low, frequency, high, low energy, and then about how long is the wavelengths. And then tell me down here, they don't give you specific specific frequencies or energy or wavelength, you can just compare it to other waves and tell me if it's higher or lower, less or more than other types of waves, okay? And once again, don't forget to add those foldables to our electromagnetic waves flap right there. Everything about the electromagnetic spectrum goes right there in that first flap in your foldable. Okay, next we turn to page 72 and we look at the properties of light. Properties of light. A light wave, just like a mechanical wave, has a wavelength and a frequency. The wavelengths of light are so much shorter and they're usually measured in nanometers. 1 nanometer equals 1/1000th of a meter. I even wrote that over here. 1 nanometer equals 1/1000th of a meter. The wavelengths of light waves range from about 700 nanometers to about 400 nanometers. This is the light that we can see. This is about 1/100th smaller than the human hair. So small. So the color orange is between 590 nanometers and 620 nanometers. That's the wavelength of it. What's your favorite color? My favorite color is about 485 nanometers. So if you can figure out what 485 nanometers is, that will tell you what my favorite color is. Energy. The relationship between energy and other wave properties is different from mechanical waves and electromagnetic waves. Now this is where it is different. The energy of a mechanical wave, like sound we were talking about last unit, is related to its amplitude, meaning the taller they were, the louder they were, the more energy they had. But so for instance, a water wave with a higher amplitude had lots of energy, those big tall waves that are knocking you down. But the energy of an electromagnetic wave is related to its frequency, not amplitude. As the frequency of an electromagnetic wave increases, the energy of the wave increases. So that's just like a little hint that on this previous page, where you're talking about frequency and energy, those are going to be related. Frequency and energy are definitely going to be related. As one goes up, the other goes up. As one goes down, the other is going to go down. Because frequency is related to energy. Brightness, brightness of light. In astronomy, that's the study of the stars, the amplitude of a light wave is related to the measured brightness of the light. The brightness of a light is a person's perception of intensity. Now, this word intensity, we had that word as a vocabulary word in our last unit. Recall that intensity is the amount of energy that passes through a square meter of space in 1 second. Intensity depends on the amount of energy a source emits. Light from a flashlight, for example, has much lower intensity than the light from the sun. Intensity also depends on the light's distance. That's very important, distance from the source. So when you're near a lamp, you probably notice that the intensity of the light is greater compared to when you're further away from the lamp. Many of the stars in this figure right here, they actually emit just as much energy as our sun, but they're definitely not as bright as our sun. Why is that? It's because many of the stars in this figure, they are much further away. These stars are less intense than the light from the sun because the stars are so far away from the earth. They're much, much farther away. Now, each person's eyes might be more sensitive to light than another person's. As a result, different people might describe the intensity of light differently. In addition, some eyes are more sensitive to some colors than others. The environment also can affect the brightness of a light. Many stars are visible in the top photo, but few stars are visible in this bottom photo. That's because there's so many light sources near the ground. In fact, we call this light pollution, where there's so much light and so much energy going around, where there's lots of populous places that have a lot of electricity, versus like if you were up to go in the mountains where there's less light sources, and then you'll be able to see more stars. All right, at this time, I want you to stop what you're doing, and I want you to go back to the CER on page 68 and record your evidence in section A. So I'm going to do that right now. I'm going to go back over here to, here we are, CER. This is on page 68, and I want you to compare the properties of light and mechanical waves. Mechanical waves are like the sound waves and water waves that we learned about in the last unit. So you can go ahead and copy my my sentence frame, or you can just write your own. So light and mechanical waves have properties such as, so what are those three properties that both waves have? We talked about them. If you don't remember what properties of waves are, you can go back to your foldable or go back in this book and look up properties of waves. And there are three main properties of waves that you should have read about. Okay, so let me go back over to, we are now moving on to how does light reach the earth, okay? When you turn on a flashlight, light is produced. The flashlight is the source of the light. What is the source of light on earth? You might say the sun, and you would be right. How does the light from the sun reach earth? Now recall that mechanical waves, including sound, they need a medium to travel through. Do electromagnetic waves also need a medium? Medium is a material, it has to go through something. So let's read this scientific text right here. Now the first time you read it, just read through. Okay, the second time you read it, you want to start underlining evidence about whether or not the electromagnetic waves need a medium to travel through. And then make connections. Obviously, we don't have many partners at your home at this time, but feel free to talk about this with anyone in your house. Or if you talk to one of your classmates online or through social media, you can use this as something to talk about. All right, using the electromagnetic spectrum. All objects in space are very distant and difficult for humans to visit. Only the moon has been visited so far. Instead of visiting stars and planets, astronomers collect electromagnetic radiation from them using a variety of tools. Radio dishes capture radio signals from space. Big telescopes on Earth gather visible and infrared light. Interplanetary spacecraft have traveled to all the planets in our solar system except Pluto and have landed on 2. No spacecraft has ever brought back planetary material for study. They send back all their information by radio waves. Virtually everything astronomers have learned about the universe beyond Earth depends on the information contained in the electromagnetic radiation that has traveled to Earth. For example, when a star explodes, as in a supernova, it emits energy in all wavelengths of the electromagnetic spectrum, all the way from radio waves all the way to gamma rays. The most famous supernova is the stellar explosion that became visible in the year 1054 and produced the Crab Nebula. You can read more about that on your own. Unfortunately, for astronomical research, Earth's atmosphere acts as a filter to block most wavelengths in the electromagnetic spectrum. Only small portions of the spectrum actually reach the surface of the Earth. More pieces of the puzzle are gathered by putting observatories at high altitudes, like on mountaintops, where the air is very thin and dry, and by flying instruments on planes and balloons. By far, the best viewing location, of course, is outer space. So if you ever get a chance to go to space, that's the best way to look out into space. It's page 73. Just a little bit more to go here. One last page. The Earth Science Connection. Recall that outer space is vast emptiness with very few spots of matter between. The space between is a vacuum. A vacuum is a volume of space that contains little or no matter. For sunlight or starlight to reach the Earth, the electromagnetic waves must travel through a vacuum of space. Electromagnetic waves do not need matter to travel. They also do not create a disturbance in matter like mechanical waves do. The speed of light. In a science fiction movie, you may have heard, "We're moving at the speed of light, light speed." What does light speed mean? Light, along with other electromagnetic waves, travels through a vacuum at a speed of about 300,000 kilometers per second. However, light waves slow down when they travel through matter. And the speed of light in some different materials is listed in the table below. Light waves travel much faster than sound waves. I want you guys to make sure you highlight that. Light waves travel much faster than sound waves. For example, in air, the speed of light is about 900,000 times faster than the speed of sound. Well, this explains why you see lightning before you hear the thunder. You'll see the lightning before you hear the thunder because the light that's going to your eyes is traveling much, much faster than the sound traveling to your ears. So here's the speed in light waves of some materials you might know of. So in a vacuum, this is the speed of light. In air, regular air, where there's air particles, it'll travel this fast, kilometers per second. This is speed. Through water, it travels at this is light waves, mind you. Light can travel through water at a speed of 225,100 kilometers per second. And then through glass, it slows down even more. So this is air, liquid, and solid. Okay, our last section here before finishing up our CER, evidence B, is a 3D thinking. Can you tell me what, we're gonna compare electromagnetic waves like light and mechanical waves like sound. So I want you to tell me some similarities, things they have in common, so both of them, and things that they have that are different. So you want to tell me how light and sound waves, things that they both have in common, and then something that only light waves has and something that only sound waves have. That you could refer to energy, you could refer to their frequency, you could refer to their amplitude, any one of those. And then the last thing you want to do for today is you want to go back to page 68, and we're going to fill in our evidence B here. I'll move it right here. So here is our CER on page 68. And what evidence have you discovered to compare how light and sound travel through different mediums? So this is what you want to say as far as air, vacuum, solid, liquid. Light can travel through what? And mechanical waves such as sound. Think back about when we learned about mechanical waves. What can sound travel through? Okay, and you can also tell me about their different speeds if you like as well. And that's it for today. We'll see you tomorrow.